All right, welcome back. Hopefully maybe you took a little break. So let's talk about vertex form when it comes to absolute value. Vertex form. Okay, so absolute value functions are typically written in vertex form. That's what we've already seen. So f of x or y equals a, absolute value x minus h plus k, or minus or whatever. We know shifts are done. So the transformation rules tell us that h is the horizontal shift. It's telling us if we're going left or right. And k is the vertical shift. We're going up or down. Okay. These shifts describe the location of the vertex. The vertex of an absolute value function is the point h comma k. You actually don't have to graph it to figure that out. The slope of the line of the right side of the vertex is a, and then the slope of the left side is the opposite, negative a. Notice how h seems to have the opposite sign in the function as it does in the vertex. So make sure when you go to plug it in, it's a negative here, but a positive in the vertex form. All right, so like always, I'm going to do the first one, pause the video, and then you can do the second one, and then check your answer. So if I'm looking at A, let's talk about my value that I'm working with. So my slope. So here I have my h, I have my k. So my vertex is actually -1, -4. All right. Then I'm talking about my slope. My slope is my value of a that I circled. So on my right side, and I'm going to label it m sub r, my slope is 2. My slope on my left side, which I meant to put an L, not an R, is the opposite. Change the sign, -2. So even if I didn't have a graphing calculator, I could go ahead and graph this without the need to. Believe it or not, that's what we did in years past when we didn't have graphing calculators. So we're going to plot the point -1, 4. And then our slope is 2. So up 1 over 1, up 1 over 1, up 2, or sorry, meant 2. You know what I mean. And then I continue. Like so. Okay? All right, pause. Do number B. And I'm going to do it here. All right, we have a vertex of -5. We have no value here, so it's just 0. We have a value of m of 1, because there's an imaginary 1 here, so -1 for r, and then my slope for the left is a positive 1, because it's a double negative. So let's plot that vertex. 5 and going down with 1s. Like so. And then you've plotted your absolute value by hand. All right, example 4. Graph each absolute value function within the given characteristics, then write the function. F has a range of -infinity to 2, has symmetry about the line of x equals -1, and has a y-intercept of 0. All right, so we know it has a range of -infinity to 2. So range, let's put that to the side. With the bracket. So we know it stops dead in its tracks. We know it has a y-intercept of 0. That's there. And we know it has a line of symmetry at x equals -1. So we know the range is here. It's going to stop at our value of 2. Ooh, and that's 1. What am I doing? Need to draw, or let's highlight. I'm going to have an axis of symmetry here. Dash that line. And then I have an axis of symmetry. Axis of symmetry at a line x equals -1 just means that there's an invisible line there and that your your graph, if you fold it hot dog style, would fold on top of itself. So at -1, it's right here going down. Okay? So then from that, we're going to graph and plot our points. So wherever it has a stop at range, but then we have the ability to see that we have an axis of symmetry and they cross, this is going to be our vertex. So our vertex is here, and then our absolute values are actually reflections on top of itself, like we learned on the front page. So then we know our second point is going to be reflected here, and we continue to write our absolute value as an estimate there. From that, we can look and see what the equation of my absolute value is from the origin. So we're going to start with f of x equals, we know we shifted left 1, so inside my absolute value, I'm going to have an x plus 1, and then a addition of 2. And then I'm going to take a second to look. Is my absolute value 1 to 1? Well, no, not really. It goes down to and over 1. These have a slope of 2. From this first point to this second point, I rise and run 2 over 1, which is 2. And so I need to make sure that's my right side. So on my, it's a negative slope, my bad, -2. So then that means I have a -2 on the outside for my value of A. Super neat. So think, if you have any questions I'm not quite touching on this video, just write them down, and hopefully you can answer them in part B, and I'll go a little bit slower in part B so you can really understand. So take a moment, try B by yourself, and then we'll do B together. Okay, let's do B. G is positive over the intervals, -infinity to 2. So it means they're positive values from -infinity to 2. And 4 to infinity only. So that means at 2 and 4, it's shooting up, right? We don't know what our values could be under the x value, but we do know we have positive values here. And it has a minimum value of -3. That should be very important. So if I have an absolute value graph here at my -2 and my 4, and this point goes directly in the middle right here, it has a minimum value of -3. I'm then needing to drop down to -3 in between, because it has to be perfectly in between to be absolute value. So I go down, and I go here. So that's it. I did my absolute value. Super quick. So take a second, rewatch parts if you need to. But this is the function of g of x. I check my slope, so my value of A. So I go up, oh no, I erased it. Hold on, let me go back. There you go. Okay, so from our parent function, our vertex form, we need to find A, H, and K. Well, if I hop down here, I go rise over run. I'll use a different color. Rise over run. I have 1, 2, 3 over 1. So that's my right side. So I know it's going to be a positive 3. Absolute value, I know an x is always going to be here. Now, I go to the right. So normally when I do a transformation to the right, and always, I'm going to go -3. And then I go down to where my vertex point here is, and this is a -3 as well. And then I'm done. Yippee, yay, amazing. Okay. Do you have any questions? Pause if you need to. Write down your questions. Rethink this if you need to. I'm going to zoom out so you can take a second. Again, we're following the parent function of f of x, a, x minus h plus k, where this is our slope, this is our horizontal shift, this is our vertical, and it is our vertex as well. vertex. So that is the reason why I'm pulling all these different values from the graph. This information leads me to be able to find my function through that notation. So take a second if you need to erase them and redo them, or look onto the homework, practice on the homework. All right, last one, best one, application problem. So example 5, the function a of L minus 3 absolute value represents the absolute deviation in meters of an adult manatee's length in meters. From the average length of an adult manatee, the function c of L minus 1.2 absolute value represents the absolute deviation in meters of a manatee's length at birth. From the average length of a manatee at birth. Okay, sorry. Didn't say that quite correctly, but you know what I mean. So from our normal function right here, and then the deviation at birth. Okay, so interpret and compare the vertices of the graphs in the context. So when we're talking about A of L, I'll do different colors. Let me erase this and I'll highlight in the colors that I did. So we'll do pink and then we'll do purple. Those don't really have much difference, but you'll be able to tell. So the pink one, my A of L, I'll zoom in. My A of L, we can see right here, the 3, that's the vertex. And so my vertex is 3, 0. Therefore, the average length of my manatee is 3 meters. That's the value of x that it holds at the average. It represents the function. So what does that vertex mean? Well, it means what I just said. The average length of an adult manatee is 3 meters, okay? Now take a second. You do the child length. Okay, found it. Found the vertex 1.20. That also tells me that average length of a manatee at birth is 1.2 meters. Oh, not an adult. Oh no, highlighting wrong things. Okay. My screen's freezing a little bit. Okay, bear with me. We're almost done, guys. Length of a manatee at birth. Okay, so vertex for my manatee, vertex for my manatee at birth. And so let's compare them. And let's see. So if I'm talking about the difference between them, well, the average length of a manatee at birth is 2.8 meters less than the average adult. Okay, so we're just interpreting the two functions, okay? Now, it's asking us to compare the absolute deviation for an adult manatee and manatee at birth that both have lengths of 2.1 meters. So they're telling me that an adult has 2.1 and a child, and we're going to compare the deviation between them. So all we have to do is plug in the length for 2.1. So adult 2.1 minus 3, that is 0.9. And then we have our child manatee, 2.1 minus 1.2. Oh, and I almost used parentheses. Okay, so take a second, look at those numbers. Well, through comparison, a manatee of length 2.1 is 0.9 meters away from both average adult and manatee birth. That's the difference between them. They gave us the same number, but the difference is if I have a manatee of 2.1 meters, it's 0.9 from the original for adult and then 0.9 from average of child. And that we're going to write, because we're talking about a real world situation, a complete sentence. Of length 2.1 meters is 0.9 meters away from both average adult and manatee at birth. Okay, and that's it. All right, I know videos are kind of tough to talk through. I try to not make them so long, so I'm pretty straight to the point. Pause it whenever you need to. If you have any questions, feel free to reach out, and I hope you guys have a good time and good luck on your quiz on Friday. Bye.